Congratulations, you've made it. This is the final presentation on trigonometry, and Pearson's, the textbook I'm taking the screen clippings from here, have called this Advanced Trigonometry. So you should be really feeling good about getting to that advanced stage. And I call these three-dimensional problems because, as we can see with this diagram up here, it's three-dimensional. Looking at this tower, could be a TV tower or a wind farm tower or whatever, from two different angles, and trying to work some stuff out there. Over here, what do we got? Oh, we got a laptop, and did you know there's a maximum distance between the edges of that, so that you will get your reception from your microphone and your camera and so on. There's a maximum distance allowed there. And what about this one down here? Let's say if you're into plumbing at all, this would be an interesting problem to see how far what's the length of rod to get into that blockage in the pipe. Stuff like that. That is interesting. And so I think this will be the most interesting set of problems that you can take up the challenge with, because you're going to be able to do really practical problems as a result of this last unit. And there's no new concepts. It's just saying, are you good enough to identify the triangles you might want to use and then hit it with trigonometry? And you're getting good at it. So let's have a look down here now at the Pearson's introduction to this. Here we're saying that if you have a three-dimensional problem, you'll probably use more than one triangle. That's why you need the go-between idea. And you also, I think, need to write out the triangles, write out the triangles separately as you go, so that you can see what they are. So if, for example, we're looking at this problem over here, we might have a triangle also going back into the figure. Remember the stuff we did on Pythagoras? The idea of working around a figure, and if there's several triangles involved, a go-between situation, we might draw them upright out here first and then put them all together. So that can be useful. All right, so let's go and have a look at the sorts of things we can do. Let's have a look here. A cube. Now, you might say, hey, there aren't too many cubes in my life. Hey, ice cubes? No. You try looking at a bag of ice, mate. I don't think they have cubes anymore. They've got these little circular things. But anyway, cubes do occur, but rectangular prisms occur, like a room that has a length, a breadth and a depth, or a height, if you like. So these diagrams up here are pretty well right on the sorts of shapes we're looking at that we live in. Okay, they mightn't be perfect cubes, but the idea of this one over here, where we've got a triangle standing up in the middle of that shape, and this one here, what would we do you think? We would pull that dude out of there. Alright, so don't have it sinking back there. Pull it out and let's take a better look at it and label the sides. And that's what they're saying here. Don't try to work with the triangle in situ, in the place where you find it in the diagram. Pull it out and let's have a look at it in flatland, 2D land. Easier to analyse. Okay, helpful hints there from Pearson's. Good hints. Let's have a look at an example. Hey, you've seen something like this before using Pythagoras. Here we are, this is a pyramid. Haven't been there yet myself, but they reckon they're good over there in Egypt. Pretty hot over there. I don't know whether I like the food, but maybe one day I'll see a pyramid. This one will have to do for the moment. And let's have a look. We're asked to find the angle the sloping edge makes with the base of the pyramid. So that's like this angle here, mate. And they would all be the same, wouldn't they? Something like that. We come down here, maybe just hang on, just there. We don't need it right to the bottom, just to that line there. Okay, so what do? Let's pull a triangle out, and the triangle that Pearson's have pulled out is this one here that I've first played with. that one there. Let's pull that out and take a look at it. We know that's 15, 90. We don't know the angle there. So here you can see we're going to need a go-between, because to find the angle we need another side. So let's go back in like we did with Pythagoras and say, is there a side we can find? And if you look at the figure above, if you go to triangle BDE, so here we are, BDE, you can see there, and we've drawn it down here, that this FD side, which is there in the figure, is half of that long side, because a pyramid is symmetrical. It's got a square base. So this diagonal going through here has two equal sides. It is split in two by the centre of that pyramid. So we're going to use DF as a go-between. So we're going to have to go off and actually use this triangle, which is laying down in the base there, first of all. Now let's have a look. It's not a bad triangle to use, because it's a square base. It's 10 by 10. This is 90 also. So by Pythagoras, I wish they would put this in brackets. By Pythagoras, BD squared, the square on the hypotenuse, equals the sum of the squares on the other two sides. So BD is root 200. Should put that BD is greater than 0, because the answer to a squared equation like that is twofold. BD could be positive or negative root 200. A negative times a negative is also a positive. We're not going to put a negative answer down, because we know here in this practical problem BD is a length, and a length must be positive. So I only put one solution. But we should explain mathematically here why we've only put one solution and not considering the negative. All right, so now DF is half of that. So we're ready to go back in our original triangle. And they were a bit naughty here. I reckon you should have your ADF triangle drawn again. This was 15. This was the angle we wanted. And now we actually have got that bottom. We've used the go-between side, yep, there, to find that 200 on root 200 on 2. So let's list down what we know. We want the angle, we don't know the opposite, we go to the 90, this is the hypotenuse, and this one here then is the adjacent. So what do we know? The adjacent was our go-between. We went and got that and came back. We know the hypotenuse is 15, and we don't know theta. We write down SOHCAHTOA. If we write down SOHCAHTOA, we have the adjacent and the hypotenuse. So the cosine is DF over 15. DF was our go-between. So we can actually stick DF in there, which is on the calculator, shift cos bracket root 200 divided by 2, and then keep going, divided by 30. Okay, doing it like that will enable us to work all of that out. The book is divided by 30 there. Oops, sorry. Well, we should be dividing by 15, shouldn't we? Because we have a 15 there. They put their 2 in the bottom line. So have a look at that. So what do you think there? Can you see that? So yeah, it's important to use a bracket there, dividing by 2 and then dividing by 15. So we're working actually the top bit out here. Let's have a look at it. That is our DF. Then we're dividing it by the 15 that was already here. So check that out. And if you do that, we get this angle, and then we round it to the nearest degree. And because it was a worded problem, we introduced our x's and our y's. We should state the answer in the context. The sloping edge makes an angle of about 62. We say about because we have rounded it to the nearest degree. Any rounding we should refer to as an approximate answer, because of course the decimal did keep going. Well, that's interesting. Very helpful if you're going to Egypt. Okay, let's move on. Let's have a look now at a different sort of problem. Oh, another pyramid. I think the writer of this course is maybe Egyptian or just loves the pharaohs or something. So here we go. A right pyramid ABCD stands on a square base. Okay, so there we have AF is the perpendicular height. Find the angle that the sloping end makes with the base round the nearest degree, hence find the height of the pyramid. So you can see it's a pretty similar sort of problem now. It's the same one with just a part B to it now. So we'll do the part B going on from the original part. So here we have what do we have here for our height? Well, we really do need to draw that triangle out again, I think. So here it is another go-between problem. Let's just make this a little bit. This is 15. We've just done the first part, and this is F and A and D. So did we find DF? Yeah, we had DF before. Have we got now AF? So what we need here is this height AF. So did we find our angle? What have we got in this triangle? Yeah, we had DF. We could use that actually, and Pythagoras, or we could use this angle that we found before without rounding it, the go-between angle. Okay, we could use that. Now what have you got? You want this height, which is the opposite side. You have the hypotenuse, so let's list it. They haven't listed it here. We've got theta is 61.87. Don't truncate it, don't round it. We want the opposite, which is h. We've got the hypotenuse is 15. So writing down SOHCAHTOA, we have, what have we got? Opposite and hypotenuse. So over here, it's the sine, 15 sine, put it in all the decimal places, and then round it. Now, did you want to do that, or couldn't we? Do you remember we had DF from up here? Where is DF? Let's go and find it. There's DF. So can you see that we could do this with a Pythagorean approach? Let's go down here. As Pearson's made this comment before. This is root 200 over 2. This is 15. So using Pythagoras, 15 squared equals root 200 over 2 squared plus h squared. Okay, I mean Pythagoras in brackets. So what have we got? That's 225 equals what? When you do this on the calculator, I'll just do it quickly for you. That comes to root of squared, it will be 200 over 4 or 50. So you could do that on the calculator. Subtract that to get h squared, which is 175 equals h squared. And if you take the square root of 175, running out of room now, equals h is greater than 0, you will get the same answer of 13.23. So I don't know. What do you want to do in that last bit? This is the trigonometry approach, but we did have DF and a right angle on 15. So you might use Pythagoras there. What do you think? Think about that one. Let's come down. Here Pearson's have got a good problem-solving strategy. This is true for all of them, not just 3D. Draw a diagram, identify right-angled triangles that contain the unknown you want that will help you identify it, redraw them, and solve these triangles using trig ratios and/or Pythagoras' theorem. So in this last one, we could have used Pythagoras as well. You got the same answer. So yeah, pulling the triangle out of a 3D shape is a useful tool. We did it in Pythagoras' three-dimensional problems as well. So have a look at always having a technique. I would say the key thing is you can always say about maths is know your work. It's hard enough to work out the actual problems. Know your work. Know that, hey, I've got a strategy, a method I'll always use to approach these problems. And at least I know that. And then as I work through it, I might come across other stumbling blocks. But I know my work well enough to draw a diagram, bring out the triangles that I need to work with, label the diagrams with all the information, and so on. Okay, let's go down and see how good you are. Here's your chance. Solving three-dimensional problems. So I've put the solutions down the side now. That's going to be easier doing one at a time. Please remember, draw each triangle that you're going to use, each triangle separately, so that you can study it, find any go-between sides, and work from there. Okay, so as you go down, there are the first three questions, and we've got the answers here for you. Just the answers, not showing the working. So here, you will in some problems need to work out how to get a 90 degree in the triangle. Things like in an isosceles triangle, the perpendicular from the vertex to the base bisects the base. That sort of thing might be useful. Don't know, you have to think about that one. Here there's a couple of right angle triangles. So try to draw the triangles separately and analyse it. Okay, let's go down to question 4 and through 6 here. I think we can fit those on. Or 4 and 5 and part of 6. 6A and B. So pause the presentation as we do this and then have a go, or use the textbook. And just finishing off 6, let's bring 6 in there. 6 then, and going to 7, we'll bring in 7, 8 and 9 perhaps. I don't know whether we can fit 9 on there. There's 7 and 8, the answers down the side. Drawing the triangles, look, here's our plumbing problem. You need to pull out the triangle. Can you find a triangle? I don't know, somewhere like that. Pull it out. Here's the other one. Add on the introduction. Couple of triangles there. Redraw them so they're flat and you don't get confused in 3D land. Right, let's go on. Oh, question 9, 10 and 11. Okay, so you can pause that, have a go, get the information, draw your diagram. Number 12 and 13. Come up here through to 15 there. Alright, so then might have a look at 15 and 16. So you can toggle it back and forwards, pick up those answers. And then the open questions, I think that's it then. We've got question 19 there. 17 and 18. No need to do all these, you're going to run out of time. And then the last one is number 19. So you can see there, if you can get through a number of these 3D problems, you're doing very well. It is getting on to the more advanced applications of trigonometry, So you can be very proud of your efforts so far now. So that brings us to the end of the presentations on trigonometry. So I encourage you to have a look at the Pearson's textbook. They've got some review questions at the end and some summary notes and things like that. So have a look there. Congratulations. Go back and have a look at some more problems if you like. But well done, and I hope to catch you in further presentations. But for now, remember, it's cheers from me.